Alright, hello everybody. I know this is not how we usually meet, and some of you don't meet with me anyway, but this is going to be the explanatory video for Lab 10. Sorry, I'm using a different version of the lab book. This is Lab 10, LRC circuit response. So in this lab, we will be kind of exploring unique phenomena to an AC current. We've used AC current previously, right, both AC and DC, but this time we're looking at something that only shows up in an AC current and is characteristic of AC circuits in general. So this is kind of the abstract diagram of the circuit we'll be looking at. We have an AC power supply, we have an inductor, capacitor, and a resistor all in series, which is why it's called an LRC. It's out of order, but that doesn't really matter. So what we are concerned about is resonance, which is very closely related to this idea of impedance, which is denoted by the letter Z. This is a whole circuit analog to resistance in a DC circuit, right? So obviously voltage in an AC circuit is constantly changing, right? That's by definition. So what we end up instead of with Ohm's law, which is V equals IR, we have this sort of analog here where we look at the electric field, right? So the maximum electric field is equal to the maximum current times the impedance. So this is kind of our analog to Ohm's law. And if we want to then actually calculate the impedance, remember it's a whole circuit analog. It's not an individual component analog. So we have to account for the resistance, right? So we've got this R squared plus the quantity of the difference between what is called the inductor reactance and the capacitor reactance squared. So something that looks kind of like Pythagoras' theorem, which I won't go into it, but it kind of makes sense if you, depending on how much you know about the background stuff, right? We're dealing with vectors and things like that, so there's directionality. So there's a reason this looks like Pythagoras' theorem, but I'm not going to go into that. It's just something for you to be aware of if you're kind of interested or to relate it to other classes. So these XL and XC is the reactance. This is the component analog to resistance in a sort of less direct way, right? So it's called reactance. It's how the circuit component reacts to the current going through it. And we have two separate types of responses, right? So we have the capacitor reactance, which is this inverse relationship, right? So it's defined by the capacitance and omega here, which is the frequency of the AC signal, right? So in other words, as you increase the signal, the capacitor reactance goes down towards zero, right? As the denominator gets bigger, this value gets smaller. We have the opposite relationship for the inductor, right? So the inductance and the frequency are just on the numerator, right? So it's divided by 1 here. So as the frequency goes to 0, the reactance, the resistance goes towards 0. And this kind of intuitively makes sense to us, right? So if we think about what a capacitor is, right? If we just look at its diagram, it's a break in the wire, right? So for a DC circuit, which doesn't have Maxwell's equations to take advantage of, right, it makes sense that at 0 frequency, we have some sort of very different response or no response at all, right? Because it looks like someone just cut the wire. Inductors are also, again, kind of intuitively make sense, but inductors are less well known. So the important thing about an inductor is this coil, right, produces a magnetic field. And how big that magnetic field is dependent on the flux, the rate of change of the flux, so of the electric field passing through this, right? So other labs will cover that more directly, but what the takeaway is the faster the electric field is changing, the stronger this magnetic field is, right? And if we think kind of more broadly about physics, nothing is free. So that magnetic field takes energy. right? So the more of the energy, so you have some fixed amount of energy from your power supply, but as you increase the frequency, this magnetic field is sucking up more and more of that energy. And so that's why it acts as a resistor, because energy is being diverted from the current flowing through the circuit into this magnetic field, which just hangs around the inductor, right? So as the frequency increases, our resistance goes up because it's all being sucked up into the magnetic field. Again, there are other labs that kind of go into that a little more explicitly. So the big thing we're exploring today is, or I guess not today, but with this lab is this idea of resonance, right? And so what we can say is at resonance, the reactance of the inductor and the capacitor are equal, right? So we've got this omega res, right? So the frequency of resonance. We can go through just some very simple algebra, and we get that this resonance frequency is defined by this quantity here, the square root of 1 divided by the inductance times the capacitance. And so what we're interested in is figuring out that. And the way we're going to do that is we're going to take a ratio between the voltage across the resistor and the voltage across the resistor and the total voltage, right? So it's going to be less than or equal to 1. And the way we're going to do that is there's a second video that kind of shows what this looks like on the oscilloscope. But this relies on exploiting the fact that there's something called phase, which is associated with different AC components, right? So in a similar way to how, if I go over here to the blackboard space, if we have y equals x, right, we've got some line going through 0. We can have the same line shifted, say this is 5, we can say y equals to x minus 5. We can shift it to the left, right, y equals x plus 5. We can shift it up and down, we can shift it around. You can do the same thing with a sine wave, right? We can say y equals sine x, or we could shift it, I'm not going to be able to draw this super well, right? We can shift it over to the left, right? And we can say this is y equals sine of x plus 90, right? So you can see we say we've shifted over 90 degrees. It's the exact same process, it's just with sines and cosines and angles, this quantity has a special name. That special name is phase. All right. So if we look at the individual components, it turns out that if we look at the voltage across a capacitor, it is at phase minus 90 degrees from the resistor. If we look at the voltage across the inductor, it's at plus 90 degrees. So we say the capacitor lags the circuit by 90 degrees, the inductor leads the circuit by 90 degrees. And what's important is, if we go back to our reactance equations, right, resistance doesn't change with the frequency. So this is a fixed value. In contrast, the reactances of the inductor and the capacitor do change with frequency, right? Which means at different frequencies, these two components will be much, much larger than one of these two components, will be much, much larger than the other component. And in specific, right, if we have low frequencies, right, 1 divided by a very small number is a very big number, right? That's how division works. So at low frequencies, the capacitor dominates, which means the signal of the whole circuit, the signal of that, of what makes it across the resistor, right? Because the resistor is after the inductor and the capacitor. So what happens across the resistor is going to shift left and right based on what happens up here, right? Because this stuff affects the circuit, and then it gets to the resistor. So by probing across the resistor, we can see which one of these two is dominating, because it's either going to lag or lead, because the resistor doesn't lag or lead at all. It's at 0, right? So at low frequencies, the resistance, the reactance of the capacitor is much, much larger than that of the inductor. And right, the resistance doesn't care about frequency, so the signal across that resistor is going to be shifted left, and it's going to be smaller than the total signal, right? Because we've got some value for resistance plus some value for reactance. If we go think about kind of like our Ohm's law equivalent, as long as these two, one of these two, or sorry, as long as the difference between these two is not 0, impedance is going to be bigger, current is set by us, it's a fixed value that we determine, which means the voltage or the electric field has to go down. So outside of resonance is where these two zero out, which means this value Z is the smallest, which means this value is the biggest, right? So going back to what we'll see, right? So at low frequencies, we'll see the signal across the resistor will be smaller and it'll be shifted to the left. At high frequencies, the opposite occurs, right? 1 divided by a big number is a very small number, but a big number is a big number. So the inductor dominates at high frequencies. Again, going back to it, the higher the frequency, the larger the magnetic field, the more energy it sucks out of the circuit into that magnetic field. So instead of shifting left, it'll be smaller and shifted to the right. At resonance, right, these two are the same, which means the difference between them is 0, which means inductance is resistance, and since it's just resistance plus nothing else, this value is minimum, right? So this value is minimum, which means this value is maximum, and this value is indirectly related to the voltage, right? Or it's directly related to the voltage, but it's not in the equation, but a maximum, the larger value of the electric field means a larger voltage, right? So again, there's a second video that shows I sweep across the frequency spectrum, and you'll see there will be channel 1, the yellow line, is just going to be a constant value because that's just reading the input signal. Channel 2, the blue line, will start out small and to the left. It'll shift and match, and then it'll be small and to the right. And what you'll do is we've provided you the voltage values at each of the given frequencies. And what you'll do is you'll go into Excel, OpenOffice, whatever spreadsheet program you prefer, or do it, well, you'll want to do a spreadsheet program because you have to produce a graph, right? And you'll find the ratio between the two, right? So you'll do the ratio of the voltage across the resistor divided by the voltage of the whole circuit. And so what you should end up with is a graph that it's small at 0, it's got, some lines, and then it'll come back down. And so this point here, when the voltage across the resistor is the same as the total voltage, which means you're at resonance, in theory, this is going to be a ratio of 1, right? Because you're dividing two things that are the same value. In practice, you'll see that maybe you don't quite get to 1. Maybe there are 2 or 3 frequencies that both give a ratio of 1. So what you'll have to do is you'll have to kind of look at the data as a whole and make a judgment of, either if there's multiple frequencies that give a ratio of 1, you'll have to make a judgment of which one is closer to the actual resonance frequency. And you can kind of, you'll just have to look at how it's changing. Either just take the middle value if there's like an odd number, or if there's an even number, maybe average the two middle values, right? That's part where you'll have to think about what is the best way to do this. If there isn't a value that's exactly equal to 1 or very, very close, you'll just have to take the closest value. As kind of a helpful hint, because there is kind of one of those more abstract post-lab questions, it asks you why when you do this ratio graph, you'll see it's not symmetric about a point, and it's not like a neat Gaussian or anything like that. And it's asking you why that is. And my hint towards that would be to think about frequency in general and think about what frequencies make sense. And you could also look at it from the point of view of look at the capacitor in specific and say there's at least one frequency that's not allowed for the capacitor. So there are bounds on what frequencies are and are not allowed, which means you will have a asymmetric graph because those bounds are not symmetric. One final note is on this graph I write time and angle as the two different axes possible. That's because you can think of phase either in terms of the time difference or in terms of the angle difference. The values given in the data sheet are for the angular difference, right? Because that's a fixed number independent of the system. So a capacitor always lags by 90 degrees. But how much time is between this point and this point, it depends on the system. So the angular phase is system agnostic, if you'd like to say, if you want to say it that way. But the time phase does depend on the system. So we're using the angular phase to not worry about errors in the setup or anything like that. Yeah, I think that's pretty much everything. And TAs should be doing Zoom meetings during regular class hours, so make sure to come to those if you have questions. If not, just the usual, email your TA, all kind of the usual channels. Thank you.